In this video, we're going to look at exponential and logarithmic graphs. We looked at these as basic functions, but now we're going to expand upon that and look at transformations and how that affects the properties of the graphs themselves. So let's start with an exponential function. An exponential function is any function that can be written in the form of y equals a times b to the x. The key to an exponential function is that the variable is the exponent. For our purposes, we will say that b, the base of the exponent, is always greater than 0. If it's less than 0, it's not a continuous function, and b will not be 1 because if b is 1, it's a constant function. If we kind of take a look a little bit at the graph of the exponential function, here we have y equals ab to the x. If I change the value of a, what you should notice, hopefully, is that your y-intercept is changing. So whatever my value of a is, that is my y-intercept on this graph when it hasn't been transformed at all. If I get to the point where a becomes negative, then we have reflected over the x-axis, and now we can see that the a value is still the y-intercept, but it is a negative value, so that's why it's been reflected over the x-axis. So when my a value is negative, you can see that my range would be negative infinity to the asymptote, and then when my a value is positive, my range would be from the asymptote to positive infinity. On the other hand, if I change the b value, you can see that as I change the b value and I make it larger, my graph is just increasing more quickly. If I make it smaller and we go past the value of 1, then our graph becomes a decreasing function instead of an increasing function. And then again, if we go into the negatives, the graph disappears because it's not a continuous function. So that's why we're restricting our b value to be greater than 0. So when it's 0 as well, you just get part of a line there on the axis. So b will always be greater than 0. If b is between 0 and 1, then my graph is decreasing. Once I pass 1, then my graph is increasing. And that's just what's going to change based on that b value, the base of the exponent, and then the a value is changing the y-intercept of the graph, and it's also affecting my range. So next we'll take a look at the graph of the logarithmic function. So a logarithmic function is any function that can be written in the form y equals log base b of x. We would also see that natural log x when we're using log base e. Sometimes we'll just see log x when we're doing common log, which is just log base 10, remember. Here, our domain is restricted to be greater than 0, so my argument here has to be greater than 0. Again, b is going to be greater than 0, and b would not be 1. All right, so taking a look at the log graph, here we have just sort of a basic log graph. We have a times log base b of x here. So if I change a, you can see that we're basically doing a vertical stretch there, or we can do a vertical shrink. If I make a negative, then we're going to reflect over the x-axis, and then we become a decreasing function instead of an increasing function here. Also, if we change the b value and we make that greater, then we're just sort of moving quicker to the left. If I take my b value and I make it less than 1, notice that again that becomes a decreasing function from an increasing function, so it's almost doing that reflection over the x-axis again. And then if we go into the negatives, then our graph goes away because it's not a continuous function. Notice that this graph has a vertical asymptote on the x-axis, whereas the logarithmic or the exponential graph had an asymptote on the y-axis, had a horizontal asymptote. All right, so taking a look here, we have an exponential function. So we know it's an exponential function because it's sort of coming towards the x-axis here as the asymptote, and then it's increasing up to the right. So I can move this point along the graph here, and eventually we'll see the inverse point pop up. So here we can kind of see the inverse point pop up there. So I'm just going to animate this point. So the blue dots are the inverse points where the x and y coordinates of the point that is the red dot is switching. So the blue dots are sort of forming the inverse graph. So we can see that the graph of an exponential and then this blue graph is the graph of a log graph are actually inverse functions. So we're getting the log graph from the inverse of the exponential function. So the exponential function and the log function are inverse functions. So a quick review of our exponential function. Remember, it has domain all real numbers. Its range is from 0 to infinity without any transformation. It is continuous. The asymptote is at y equals 0, and my intercept, again with no transformation, is the point 0, 1. And then quick review of our logarithmic graph. It has domain 0 to infinity because it's not going to the left side of the graph there. The range is now all real numbers. It is continuous over its domain, which is only from 0 to infinity. The asymptote now is a vertical asymptote at x equals 0, and my intercept is 1, 0. So remember, both of these are before any transformations. All right, so taking a look at the exponential graph and transformations, so you can see up here we have this equation a, and then I use the base of e. We could use any base here, it's not going to matter. So a times e, and then my exponent is 1 over b times x minus h plus k. So as I change a, remember we did this before, this is changing my y-intercept, and if I change that to negative, then that's going to change my range, because instead of going to positive infinity, we're going to negative infinity. So a is my vertical stretch or shrink, and a is going to affect my range if it's negative or if it's positive. It's also changing my y-intercept, but that can also be changed by a couple other things too. Just going to set this. So now if we look at this b value, so I'm going to change the b value. This would be my horizontal stretch or shrink. Notice that between the equation and the value, we're taking the reciprocal. So here I'm doing a horizontal stretch. Come back. Here I'm doing a horizontal shrink. If we make this negative, then we're going to do that reflection over the y-axis. So this is my horizontal stretch or shrink, and when it's negative, we're flipping across the y-axis. The h value up here, so this is x minus h, remember, so this is going to be my horizontal shift, so I'm shifting left or right. It kind of looks like we're stretching it, but technically that graph is moving to the left or to the right. And then k is going to be my vertical shift, so we're moving up or down. And notice that that k is going to change my range because it's also changing my asymptote. So my properties are coming from that k value. As I change this, it's not changing any of my properties other than that y-intercept, but my domain is staying the same, my range is staying the same. Looking at the equation that we had in Desmos here and talking about the transformations, a is my vertical stretch or shrink. Remember, we talk about vertical stretch or shrink with a positive value, so it's the absolute value of a is my vertical stretch or shrink. And then if a is negative, then that would be a reflection over the x-axis. The absolute value of b would be my horizontal stretch or shrink. Again, remember this is b, but up here it's 1 over b, so we're taking the reciprocal between the two. If b is negative, then that's going to be a reflection over the y-axis. H is my horizontal shift, so I'm talking left or right shift here, and k is my up or down shift, so my vertical shift. Every exponential function has domain all real numbers. The range is going to be negative infinity to this k value if a is negative, and k to positive infinity if a is positive. So the sign of a tells you whether you have negative or positive infinity in here, and then k would be the number that's in your range. If there's no number here, then that's just going to be 0. And your asymptote will always be y equal k. Again, if there's no number added as a constant, then your asymptote is just y equal k. Similarly, we're going to take a look at the log graph. I used natural log here. We could have used log any base. So a is the number in front of natural log, and then we have 1 over b times the quantity x minus h, and then plus k. So if we look at what happens to our a value, this is going to be, again, our vertical stretch or shrink. So vertical stretch, vertical shrink once we go below 1. And then remember, if we go negative, we're going to do that reflection over the x-axis. B, now remember this is 1 over b, but b is my horizontal stretch or shrink, so this is going to stretch us in the horizontal direction or shrink us in the horizontal direction. And again, if I make that negative, we're going to flip over the y-axis. H is my left or right shift. So notice that this changes my asymptote. So my asymptote is moving with that h value. So whatever my h value is, that is my asymptote. And so if we move that to the left, then we're going to get a negative asymptote. So at x equal the value there. And then k is going to be my up or down shift. So this is really not changing any of my properties other than my intercepts. So it's not changing my domain and my range. So the big change comes here with your h value, because that's going to affect your domain, because your domain is always going to be from your asymptote either to positive infinity, or if b is negative, then it's going to be negative infinity to the asymptote. Again, taking a look at my equation here, the absolute value of A is going to be my vertical stretch or shrink if it's negative, reflection over the x-axis. B, again, reciprocal from the equation to our transformation. The absolute value of B is the horizontal stretch or shrink. If B is negative, then we're reflecting across the y-axis. H is my horizontal shift, so left or right, and K is my vertical shift, so up or down. So here I have restrictions on my domain. So when my b value is negative, then that's going to be from negative infinity to h. If my b value is positive, then h to positive infinity. So again, whether b is positive or negative tells you whether you're going to have negative infinity or positive infinity. And then that horizontal shift is what's going to be the number that's in your domain. Your range is always going to be all real numbers, and your asymptote is going to be at x equals your h value, your horizontal shift.